When an object is in free fall, that means the only force acting on it is gravity. We know that the mass has no effect on how fast an object falls when in free fall, ignoring the effects of air resistance. So if Michael drops a rock into a pond and his friend Sarah drops a rock twice as large, both rocks will hit the ground at the same time. Also, if a skydiver jumps out of an airplane and is in free fall to the ground, if he lets go of his camera, that camera will fall at the same rate that he falls. This is all ignoring the effects of air resistance. On Earth, all objects accelerate to the ground at 9.8 meters per second squared, which means the velocity of an object will increase by 9.8 meters per second each second that it falls. In other words, if a freely falling object has a speedometer on it, the readings will increase by 9.8 meters per second each second that it falls. If that freely falling object was equipped with an odometer, which measures distance, we would see that it's covering unequal distances every second because it's increasing its speed. It's accelerating. Suppose a baseball is dropped from rest and it falls freely to the ground. We could figure out how far the baseball will fall and its speed at any time if we know the acceleration and the time. We need two formulas. The distance formula is the initial velocity times time plus half times the acceleration times the time squared. To find how far the baseball will have fallen after 1 second, we will use an acceleration of 9.8. The initial velocity is 0. Then we do half times 9.8 times 1 squared, and that equals 4.9 meters. The baseball will have fallen 4.9 meters in 1 second. After 2 seconds, the initial velocity was still 0, so we can ignore the first part of the formula. All we need is half the acceleration times the time squared. So half of 9.8 times 2 squared is 19.6 meters. The baseball will have fallen a total of 19.6 meters after 2 seconds. We can do the same thing to figure out how far the baseball will have fallen in 3 seconds and 4 seconds. Let's figure out the final speed of the baseball after 1 second. Initial velocity is 0, the acceleration is 9.8, and the time is 1 second. So we have 0 plus 9.8 times 1 is 9.8 meters per second. After 2 seconds, the baseball is speeding up. So our new time is 2 seconds, but the acceleration is still 9.8 meters per second. So we have 0 plus 9.8 times 2 is 19.6 meters per second. We can do the same thing for the speed at 3 seconds and 4 seconds. The acceleration remains 9.8 meters per second squared. The title of a graph is always the y variable versus the x variable. So distance is y, measured in meters, and time is the x, measured in seconds. If we plot the data, we can see that this graph is a curve. A distance versus time graph that's a curve shows an acceleration. Let's graph the velocity versus time data. Velocity is in meters per second, and time is in seconds. Connecting these points, we can see that as time goes forward, the velocity is increasing at a constant rate. When we graph the acceleration versus time, acceleration in meters per second squared is the y, and time in seconds is the x. We can see that the acceleration is staying at 9.8 meters per second. As time goes forward, the acceleration stays the same. Now that we have our graph, we can fill in this section. Is the object in free fall covering equal or unequal distances every second? Well, it's accelerating, so it's unequal. The velocity is increasing by 9.8 meters per second each second. The acceleration, however, stays the same at 9.8 meters per second squared. After 10 seconds, we use the same math formula, and we have a total distance of 490 meters. The ball is moving at a velocity of 98 meters per second, but the acceleration remains 9.8 meters per second squared.